Now it's on tape.
Now it's recorded tape. When people say tape, you know they're old. Tapiness.
Older than me, yes. I wasn't gonna call you like ancient or anything, Rocky G. You're not ancient by any means.
My little brother, when he was learning the definition of ancient, he's like, oh, like grandpa.
Oh. Oh.
Which I thankfully was not in front of my grandfather.
Grandpa would have been like, oh, what? Lavina, you're like 19. Wait, are you 19? No, I'm not. How old are you?
21.
21. What the?
Yeah.
Wait, how old are you?
You are 21?
I
Yeah.
thought you said 31. I was like,
I look really young for
a little bit
me.
shocking,
You look 12.
yes.
Respectfully, you look 12.
Thank you.
Lavina's 21.
I know, right?
I'm 21. I turned 22 in like 2 weeks.
How old am I?
50.
That's a lot. I feel like 40.
No.
35.
What?
31.
Oh, now that there's
Okay,
a guy
whoa.
who can say
Whoa.
he's just like,
Just trying to get some extra credit.
Whoa.
yeah, it's working. Yeah, I'm 57.
Oh, excuse me, what?
I didn't finish my
Yeah, I'm
guess.
57.
I knew it was 50.
I was gonna say 45 and above.
I was thinking like
I was
late
thinking
40s,
late
early
40s.
50s.
Yeah.
I appreciate it. That's good. I have a youthful spirit,
This
right?
is the
Like,
confidence that he needed today.
a sprightly grandpa. So, did anybody parameterize this?
No.
I did.
I did my.
Am I the only one?
I did the homework. I didn't do that though.
Sorry, it was a slow clap.
Did you mean it though?
That you did the homework?
Was it an actual clap? Like, were you actually proud of me, or was it like a? Oh,
I am proud of
did
you,
the
but I mean
homework.
that's the it's a little of both. Nobody parameterized this shit?
No.
I'll do it now.
No, we'll do it together.
No, it's not it. Wasn't no on like chapter 17 of the book last week, anyways.
I forgot about it.
So let's call this R of T.
Beautiful.
Indeed, I made that up myself, all myself. Imagine. So R of T is going to, as T moves from some value to some final value, I will traverse this, and I think I said do it counterclockwise. So like that. I'm going to start at 0, 0. So the first thing is, the easiest part is the first part. From 0, 0 to 1 plus I, and I gave you a couple formulas to practice with. Seems like I'm going to have to make some required things to practice with. So we'll do, awesome, yeah. So when T is between 0 and 1, and I'm just making that up. It could be anything. It doesn't matter what this parameter range is. I could do 0 to a third to 2/3, 2/3 to 1 if I wanted to be super elegant, but this gets it done. And so my first point is 0, 0, and I just need to have increments of 1 plus I between 0 and 1. Now check this out. When T is 0, I'm at 0, 0. When T is 1, I'm at 1 plus I. And this is a linear expression, so it must look like a line. So the fact that this describes it says I've got it. The fact that this has the 2 points, the start and the end on it, and it's linear, says it works. It's not the only way. There's infinitely many ways to do any of these. And so your answers might look different. The cool thing is it won't matter how you do it, as long as you do it correctly. Is that making sense? Like, do you see how that gets me my first piece? The next piece is where things get a little trickier, because up here, I said this is going to be a circle of radius 1. So up here, this looks like a circle of radius 1. Here, let me actually, so the top is a circle of radius 1. I said that like 7 times, so that's the last. Centered at I. We had this formula that a circle centered at z naught of radius r, e to the I t here, from 0 So this is a full circle right here. Does it make sense to you that without this part, that gets me a circle of radius r?
Yes.
Yeah, is that, okay, good, that's making sense. And then I just shift it by z naught, and that moves the center, which was at 0, to here. And this gets me a full revolution, but I really don't want a full revolution up there. How many radians worth of travel do I really want? Right, is this pi, right? Here's 0, and then we want to go up to pi. So I'm gonna say, okay, let's call that pi. Cool. And my radius is 1, and my center is I. So that looks great, provided t is gonna run from 0 to pi. But I've already kind of like set myself up with this 1 as the starting spot, and I've gotta pick up from 1 and keep moving from there. What I'm trying to do is take the real line, so this is my t parameter. So 0 to 1, that piece is that left segment. That's this thing right here. I would like from 1 to 2 to be the top part. And then I would like from 2 to 3 to be that final stretch all the way back home. That little piece right there. And that's gonna take me up to 3. So this is just like the way I did it, not the only way. Notice here that I can pass some of this pi-ness up into the exponent here. So equivalently, I could do I plus e to the pi I t. So I put the pi up here and then make this from 0 to 1. So now that takes me from 0 pi up to a full pi. That's cool, but that's still not quite what I want. I want this to go from 1 to 2, so I'm just gonna subtract. I'm gonna make t run from 1 to 2 and subtract 1 off in the exponent here. So if I go I plus e to the pi I t minus 1 like that, I now have that thing parameterized. And this is just one way to do it. Like I said, there's always infinitely many ways to do it. But if you understand what I'm doing here, that's the process, the thought process is the key thing here. You could simplify that if you wanted, but that's going to be to 2. And actually, usually you kind of want to leave off. You don't want to, these should be the same point, but no, I'm going to put my less thans on the right and my equals to's on the left. Except for this last one. Can you do the last piece for me? We need to travel from 1 plus I to 0 as t runs from 2 to 3. So here's a little puzzle. Yeah, Lou.
Oh, yeah, yeah.
Oh yeah, let me take a look. Awesome. Yeah. Is that, oh, that's you too there. Okay, gotcha, gotcha. One thing to, so this is we do have a problem. You got the right idea, but when t equals 2, you have a negative 1 after
Yeah.
it.
Yeah, so make it plus 9.
Oh, I see. Oh, I see. You put the conjugate there. Oh, okay, cool. And then when you got it, yeah. Okay, I think that works. Nice.
Okay.
That's cool. Oh, so yeah, you just moved the negative. So I would have done
Yeah.
3 minus t with that point, but you got the same thing. You put the negative there. Beautiful.
That would make sense.
Nicely done. Yeah, beautiful. I'll put what Lou did. Lou, could you read that to me?
Yeah, I said t minus 3 in parentheses, and then 1 minus I.
That's what Lou did. I would have done negative 1 plus I and then done 3 minus t up front. So these are the same answer. It's just that Lou's got the negative hidden in here as opposed to the negative out in here. So check this out. I know that I need to be at this point negative 1 plus I. Oh, and actually this is not quite right, is it?
Why?
Because when t, oh no, it is right, sorry, yes, it is right. I was thinking t ran from 3 to 4 for some reason for a minute there. This is perfectly right. So when t is 2, I've got 1 here and I'm at my point, and then as t moves to 3, this goes to 0 and takes me back home. So this parameterization would work. Did anybody do anything different? Because you could, I mean, you could even do something crazy like this. It's not super consistent, but you could do like t runs to 4 here, you know, or something like that, and then you just have to adjust to make sure that you're at your endpoints as you need to be. But this one's the easy. I think that's the lowest hanging fruit. So good practice. When we get into integration, this will become essential. Sydney,
It's
Clear
gonna be
your
so
throat.
much fun.
you're clearing your throat.
Right. It's gonna be so much fun.
Yeah, that's
So
it.
excited.
That's it. Do you all have any questions? We have a homework assignment floating about.
Yeah.
When does that due? Monday.
Oh, yeah, I have questions.
Me too.
Cool, let's talk.
For a second, I was like, what's homework?
The one we talked about in the group chat yesterday.
Oh, where is my homework?
You doing all right now?
Yeah, I'm doing alright.
Okay, good.
Number.
I did get some best sleep last night.
I'm sorry.
Ask the last two. I'm gonna ask the last two.
You're gonna ask the last two? Great, great, great. For number 1.27, part D, right? Yeah.
That's a good one. That's a real good one.
I'm struggling with the sketch.
Uh-huh.
So I understand that it's saying the distance between z and 1 plus the distance between z and -1 equals 2,
Yes.
but it's the picture.
Yeah, and it's pretty hard unless you like know this particular description of a conic section. And so let's get into that because it is a good thing to know. So let's see. We could do D, which one was this in E?
D.
This was D.
This is D.
So let me do E,
Okay.
which is mod Z minus 1. This is E-ish. Mod Z minus 1 plus mod Z plus 1 is less than 3. So one thing you could do is just start guessing, right? Like, what's in there? Zero's in there. And then just like keep trying, but that's gonna suck. That's gonna be a miserable, miserable process. So Sydney, the way you read it, like as the interpretation of distance, that is the way to go. So this one here is that the distance, it's the locus of all points whose distance from 1 plus their distance from -1 is less than 3. So if I took, here, maybe this can help me out. If I took a point and another point, and I put, let's imagine these are pins sticking out of the board, it's coming out, and I can take a loop of string and put it on here. So let's imagine I take a loop of string that's a little slack and kind of slides around, but I take my pen and I hold it there. And I just keep going as far as I can. What shape will I trace out as I keep my pen there in the string? Do you know this? Have you seen this? What is that shape? An ellipse. So this is how you make an ellipse. This is one interpretation of what an ellipse is that this D1 plus this D2, that distance will always be the same sum. So D1 plus D2 is a constant. That's going to give us an ellipse. So what we have here is an ellipse. You just need to figure out, and this might be the challenging part, let's think about what we know about ellipses. So let's see. So the one, notice here that these 2 points that I'm anchoring to, they aren't going to be on the ellipse. The ellipse is going to look like this. Something like that. It's appreciate it, like that. These are the foci of the ellipse. These are called the foci. So like, if you shined a light inside here, all the rays of light would end up going to these foci. So you could put like a hot dog there, and like to put some high intensity light in there and cook a hot dog. Like, have you ever seen the solar hot dog cookers?
No.
It's kind of like that. No, I think they're parabolic and not elliptical. But they have like you have like a little stick. You put a hot dog there, and then the sun's rays come down and blast that mofo into hot dog heaven. So my foci here are 1 and -1. Those are the foci of the ellipse. Figure out what the minor axis will be and what the major axis will be by experimenting with some points and seeing what actually, like how far out can you go this way? How far out can you go this way? How far straight up can you go and still satisfy, yours is an equality, right?
Yeah.
Yeah, so if we have an equality here, well, hell, I'll just do this one really quick. And then you can just kind of figure it out. So, what's the furthest we could move this way to the right of 1 and have this add up to 3? Like, what's this point right here? It might be easy. What is it? Is it 1.5?
Yeah.
Yeah, I think,
No.
yeah, that sounds right, because if z is 1.5, oh wait,
No,
or is
that's 2, isn't it? Because that's 0.5 plus 2.5.
let's see, so z is 2, then here I've got 1 plus 3, that's not gonna work. I think let's try that 1.5 really quick. So 1.5, z minus 1 would be 0.5, and then z plus, that's it.
Well, it's 2.
That adds up to 3.
Never mind, I'm wrong.
That's all good, that's all good. So, nice eye on that, Lou. So this point here is 1.5. That means this is negative 1.5. And then do some kind of similar reasoning to just figure out what that is. I'll leave that to you.
Okay. Okay.
The more painful, the thing you could do if you were a crazy math crazed person, yeah. You could go, oh, let's see, so z is x plus iy. So z minus 1 would be x minus 1, because that's real, right? So that only affects this, plus iy. And then when I find mod of that, that's going to be the square root of x minus 1 squared plus y squared. So I could replace that one with that z minus 1 mod with that, and then I could do z plus 1 is going to look like this. This will take a lot of time, but it might not be that bad. Hold on a second, we'll do that. And then add these together, set them equal to, I think you've got 2 or whatever, and then work this through, and you'll end up with an equation like this. You'll end up with an equation that's something like x. Oh no, it's going to look like this. So it's going to be x squared over 1.5 squared plus y squared over whatever. This is the number you have to find, equals 1, something like that. So you can take that all and put that into an elliptical form, because if you have this, you have an ellipse with a units on the x-axis and b units on the y-axis. That's canonical. Imagine it's good. Imagine that's
It's beautiful.
Thanks.
I was almost there.
Were you?
Yes.
Wow. Did you go? You went this route, kind of? Yes.
I
You're
just
crazy.
I just did some witchcraft in the middle. And
Witchcraft. You're funny.
I love that. That's awesome. Good for yes.
No, but like I had the x squared plus y squared equals 1. It's just I added the z minus 1 and z plus 1. I'm like, oh, both are in mod. I'm gonna just put everything in a mod. So
But it's a lot of work, isn't it?
No, not exactly. It's like 5 lines.
Not bad. Cool.
Okay.
Oh, that's much nicer than my definition of 5 lines.
Uh-huh.
Look, I'm a lazy person.
Well, you did do that the crazy way.
It's the most logical.
All right, what other questions do we have?
The same thing, see. Actually, no. No. Actually, yes.
You mean the one,
Well,
wait, sorry, 127C?
Yeah.
Okay, so here, let me give you some tips on how to think about this.
Yeah. It's just that greater than 0 for that's.
Absolutely. So what would that, let's write up your thing here. So we've got 0 less than z minus 1 mod less than 2. So what number, what is this keeping z from equaling?
0.
One.
Oh. 1.
It's keeping z from being 1, right? So this right here says z cannot be equal to 1, right off the bat. What if we just had this? So let's take a look at that. What is that? Soft, oh, I like the way you said that. No, it's a soft circle. Where's my center? 1, 0. So center here, yeah? And what's the radius? 2. So like you think about the boundaries when you're thinking about these things. Set it equal, that's your boundary. And really what we're looking for is the interior. So we're doing the interior. We know those words now. So it's a circle centered here, but I can't get to the center because of that. And then it's radius 2 all around with all the stuff in between.
So it's like a donut.
It's
Yeah.
like it's like a donut with almost no hole. A donut with just like on a skewer.
And that's
So just like a piece of naan. On
It's like a piece of naan on a skewer. Yeah.
interesting.
Okay, I'm getting hungry.
I know. Wait, you're the only one who's got food.
Eat your damn apples.
What? Okay. What else do we want to talk about?
Follow up on that same
Yeah.
part.
Yes.
Are we at any point gonna talk about or review the open, closed, grounded, and connected definitions and stuff?
As we need them, we will come back through them. Absolutely. I mean, do you want to talk about them now or?
Yeah, cause that question, the second part of that question is determining whether they're open and closed, and then grounded and connected.
Oh, okay. Yeah. Cool. So let's actually do one together then. Yeah. Thanks, Sydney. There's more stuff happening there, right? Oodles and oodles of stuff. Ooh, F looks. I'm looking at F and it's like super exciting. But let's just do the. Let's just do this one. And we can some of you have tried it and you can think it through and then you have to explain it still anyway. So this thing here is gonna be a punctured disc of radius 2 centered at 1. And soft, like Noah said, I like that. So it's a soft disc. Like that, and it's got all the stuff inside except for the center.
And not including the boundary.
Not including the boundary. That is a terrible drawing. Almost incomprehensible.
If we didn't know what you
If-
were trying to
Oh
draw,
my God, yeah.
absolutely.
Absolutely. That's a horse shit. So this thing, so we have some questions to answer, and let's go through and do it. Is it open? So what does it mean to be open? What does that mean? A set is open if around every point in the set,
You can draw a signal that's all in the set.
I can make a disk that's completely contained in the set. There is just one, right? I just need one. Once there's one, then all the tinier ones come along for free. But I have to ask myself, is this set open? So no matter where I pick a point, because of the fuzz on the edge, I can always find a disk that's around that thing, right? Because something here, like take this point here, this point Z, I take that in there, I know that Z is less than 2 units away from 1, so all I have to do is figure out this distance and I can work out the radius of a disk there. You don't need to work that out in great detail. I don't need like the exact computation for that disk, but does it seem obvious that no matter where I go, I can do that? Because that's what I want. I want this intuitive feeling for us. That would contrast if I had an edge on this thing, right? So if there was a little bit of solid edge, then this wouldn't be open because I could pick a point there on the edge and no disk is contained inside the set. There's always, because it's a boundary, spills out, spills in. So in this set here though, we can always approach the fuzziness with a tiny disk, stay inside there. So this set is open. This set is not closed because a closed set contains its boundary. So remember, so let's write up a couple things here. So this set is open because any point in the set has an open disk, and I don't know how to spell disk, right? I think we talked about that. Choose your favorite. Ooh. Has an, has an open disk, disk A, around that is contained, an open disk about it that is contained in the set. And then it is not closed because it doesn't contain its boundary. Because it's bound. What is the boundary of this set, by the way? Well, wait, say that again, Lavina, sorry.
I don't think it has a boundary, but anything less than, not anything less than 2.
So you're saying stuff inside here?
No, like all the stuff inside it, but the boundary should be like 2? Like 2, maybe?
Z minus 1 less or equal to.
Z minus 1 equals 2.
Yeah.
That is the boundary. Yeah, I was looking for more than 2.
I was like looking at.
Yeah, it's like, yeah, 2. So the boundary is if you have equality there, and then that closes it all in. Is this point, is 1 a boundary point?
That's not so difficult. Maybe, I don't know.
No, because any circle you draw around will only have things inside.
But it also, it's not in the set itself, right?
So wait, is a boundary point a puncture disk or a disk?
That's what I'm asking.
It's supposed to be a function disk.
Is this an accumulation point?
Yes.
Definitely that,
Great.
right?
I can buy that.
So let's just talk from there. So this set doesn't contain all its accumulation points either,
Right.
right? Because it doesn't contain the boundary, and these are all accumulation points. They're boundary points, but they're also accumulation points because every disk around them has stuff from the set inside of it. So you can approach that point with infinitely many, you can get a sequence of points in the set that converge toward that boundary. Same thing here. This is an accumulation point. I'm not sure it's a boundary point though, because I think you're right that it's not spilling inside and out, but it is an accumulation point. So let's write up here, not closed because z equals 1 is an accumulation point that's not in the set. The set. And also, it also doesn't contain its boundary. It also doesn't contain its own boundary. So this set is not closed. Is this helping with
Yeah.
this? Awesome. All right, so then we've got, it could be neither open or closed as well. I could make this not open by just literally adding a little part of the boundary. And now it's not open. And if I don't add the whole boundary, it's also not closed, so it's easy to get that. What does it mean to be bounded?
I can draw a big circle and get all the points inside.
Beautiful. You just draw a big circle around it with finite radius, right? That radius might be Google, but it's still a bound. So this set is bounded because I can draw either a giant circle around it and contain it, or a box. Either way, it's contained in a finite space.
Oh, okay.
Yeah, yeah, yeah. What does connected mean? You know something, I'm hearing some right words.
A set is connected if it is possible to find two separated non-empty sets whose union is G.
A set is not connected, if that is the case, right?
It is connected.
A set's connected if you can find a path between any 2 points in a set that's also in a set.
That's the easiest way. So connectedness gets very technical if we were having a topology class. Noah's just tossed out a definition that's called pathwise connected. That doesn't always mean connected in the full topological sense, but for us it's good enough. You're gonna like this one, Sydney.
Great.
It is connected because between any 2 points, I can find a path inside the set. If I can travel from one spot to the other without getting up and jumping over something, I'm connected. So even though this has a hole in it, so check this out. And later on in the class, we'll deal with these things. These are called annulus. So an annulus, even though you've got a big hole in the middle, that's still connected
You still go around.
because you can still go around. Yeah.
Beautiful.
Not connected literally looks like separate pieces. Like 2 open disks that were, maybe their boundaries are touching, but they're not touching. That is not a connected set.
Okay.
Yeah? So it's very intuitive. You've got to have the picture though to help with that.
I love pictures.
I do too. Anything else on the homework?
It's your turn now. Go crazy.
Oh, yeah. 1.29.
Yeah.
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 So 1.29 has a lot of stuff going on. So G is a set, and it's either real, and Z is either real, Z is either between -2 and -1, or the distance is less than 1.
So one of your conjunctions, you said it differently than it is here. So let's take a look at your so let me tell you what I heard. And I think this might be making it more confusing for you than you think. So G is the set of all complex numbers such that Z is real. And then it sounded like you were maybe giving that next part as a separate condition, whereas it just modifies this. So Z is a real with,
Yeah.
right? So that would make it very confusing, I would think. Did I interpret what you were thinking correctly?
I mean,
So Z's on the real number line.
Z's on the line,
Yeah.
so Z is just literally on the real line, and it's just this piece of the real line.
Thought we were doing complex analysis for that.
Hey, man. What up, bro? Do you even complex?
okay, so that R length is less than 1.
Yeah, so now we've got a whole other kind of set that we're tossing in here. Or modulus of Z is less than 1. What does that look like?
Centered at 0 and a circle with radius less than 1, like a dotted line.
With a fuzzy edge, right? So yeah, so we've got that. And that doesn't fill in that dot, right? Because that dot is at 1, and this thing doesn't get to 1, it's less than 1, so we got that, and then, so then all that fuzziness there. So far it looks like a ball with a stick coming out with a soft end.
Actually, it's -2 to -1.
What?
Like, the first one,
Mhm.
Z in real,
Yeah.
that's
You did that.
-2 to -1.
Mhm.
So shouldn't that, like, instead of being from -2 to 1, shouldn't it just be -2 to -1?
Oh.
Like,
I mean, you're not gonna see this piece because it will be kind of covered over with this disc.
no, like, you did -2 to 1.
Uh-huh.
The bounds are put a negative in front of the one on top.
It's supposed to be -2 to -1.
Oh, to -1. Oh, I see. I misread that. Gotcha.
Now
So that circle, instead of being over there, it should be on the other side, right?
Well, no, so this circle's still the same. It's just that original
So
set
like, yeah, the dot.
would just be like that. Yeah, it's just that little piece right there.
Okay.
Yes.
And then it's z equals 1 or z equals 2.
So what does that do now? So z equals 1 is just a point, right?
Yeah, a point at 1 and a point at 2.
And was it 2?
Yeah.
I missed this.
Yeah.
So it's a funky set.
Yeah, I kinda got it right. I just had like the whole
It's not
stupid line over there.
open or
So
closed.
this is a point.
Yes, so neither open nor closed. Can we kind of look at that and see that? Anytime, so this is an isolated point. Anytime you have isolated points, you are not open. You cannot be open with an isolated point. Isolated points are closed things by nature. So is it connected? How do I travel from here to there?
It's not.
You
Come
know.
outside the board and it'll space.
Yeah, because it's complex, man. Just
Exactly.
get the fuck out of there. So it's not open or closed, it's not connected. What else did they ask us about it? Also, so then they ask us, so we did the sketch, what is the interior of G? And so let's go through this. Is this in the interior?
Yes.
This point? If I make a disc around that, what disc will be
Oh.
contained therein?
Never mind. I thought it was just what is in G.
Yeah. So what does the interior of this set look like? We can actually just describe it. What is the collection of all things that, all points where I can make a little disc around them and they're still inside? Just that circle, yeah? This doesn't have interior, when you have an interior, you're thick, right? Lines don't have interior, so this has no interior, or it's empty set interior. The only interior can be that lovely open disc with all the stuffs inside. And then what else do they ask us? Find the bound, and I think I might leave you the rest now that you have the sketch. Does that sound fair?
Yeah, it helps with a picture.
Awesome, yeah, the picture, you gotta have the picture.
Is that last one?
Yeah, but all these parameters.
Any other questions, my friends? Ay, ay, ay.
I wanna say 1.33, but I also kinda wanna try.
Wait, which one, let me just see if I could give you maybe,
It's the parameterizations.
1.33.
yeah, so, I mean, using those formulas, you should be able to knock out A and B just using the formulas I gave you in class, right? I gave you like, just plug in the points and stuff into these formulas and you'll have them. I think you should be able to do C now because we kind of did that. You will have to change the orientation. So the way that I've described these parameterizations, so like if I said, oh, I've got 2e to the I, now I like to put the pi up here personally. If I did that, what does that look like? What does this trace out? And we need to get good at doing that in our heads, figuring that out.
starts on 0 and draws it out counterclockwise.
Just the top half too,
Yeah.
right? So I just go up to just the top half. How could I go backwards? So this is oriented this way. What could we do to go backwards, to start at?
-5.
Just sort of like.
T1 minus 2.
Let's try. So tell me what to write. Tell me the parameterization.
So 2e to the -I/2.
Let's try it, right? And sometimes with this, just try it. You write it out and you see, does this work? So what is my parameter range, Alina? Oh, that's interesting.
Wait, hold on.
Well, we better go up. We want to go up. Well, I kind of think you might have got it there. To this is 0. I think that might work. Let's try. Let's see. So when t is -1, we are at 2e to the I pi, which is here.
Beautiful.
What about when t is -1/2? Let's just check the halfway points, because we're kind of hoping we'll be right here, right? We're hoping we're moving that way. So when t is -1/2, I've got 2e I pi over 2, that's right here. And then when t is 0, we're sure the hell here.
Look at you, little genius.
Good job. Well done.
Witchcraft used to do that, but.
So, but that's not the only answer either. Let me show you another way you could do this. If you wanted to go backwards, you could just do this. You could say, use the same range here, but then go 2e to the I pi 1 minus t. And now, when t is 0, I'm at this, and as t progresses toward 1, this shrinks to 0, and takes me over to here. So that's another answer. Lots of answers. Cool, that's a great question. So let's see. So now you kind of see how to do that one. 1/3, did I assign all of those?
Yeah. I want A. Hold on.
No.
I feel like I did.
It's A, B, and C.
Yay! Then your life is easy. You're welcome.
Hey.
Hey!
Cool.
I understand.
Did you see some kid died from eating the 1 chip challenge?
What?
Yeah.
Okay, hold on.
What happened?
Where was your segue?
Hey! I was thinking, I don't know, that's
No, that's a bad segue. And then you followed up with, some kid died. Dr. T. We need to
What
work
is
on
the
your
1 chip
segues.
challenge, first of all?
It's where you eat this horrible hot chip
It's, yeah,
that's stupidly hot, and then you do it on camera and,
yeah,
and suffer
and try not to die.
for no good reason other than doing it.
Like, there are people
How
who
did
don't
he
even
die?
get
Is
a
he
whole
in
life
No,
now.
they're not quite sure it was the chip. Don't do the 1 chip challenge though. I guess that's like,
I have a moral compass.
well, I don't know if it's immoral.
Dude,
It's just stupid.
dude, those go hand in hand.
I don't know if eating chips could ever be immoral, unless you're like
Action.
eating them in front of a starving child, and you take their chips and you eat them slowly in front of them.
Listen,
That would be wrong.
See, I was afraid that it would try to eat the spicy chips.
That's right. But if that child was gonna do the 1 chip challenge and you took that chip and stopped them from doing it, then that's a good thing. Crazy. Crazy shit. Alright, sorry for the bad, sorry. My mind is hopping. Is there anything else on the homework, or do we kind of run the gamut?
I think we got every question.
We got everything, awesome.
So, for 1.23c,
Yeah.
I think I got it. It's like, it's a set where the real part of z plus 2 minus 2i equals 3. So I just did like z equals x plus iy and then did the whole thing and then just took out the real part and was like, yeah, that's equal to 3.
Perfect.
And then it's kind of like this straight line.
Yeah, Yeah, you're absolutely right. So in that one, yeah, you did the right move. Convert z to rectangular form, x plus iy, and then just think in the plane. Perfect. Perfect. Cool. Well, I want to start a little bit on the next section. I'm definitely going to recommend to you to start reading chapter 2 if you haven't. I'm also going to recommend you go to that complex-analysis.com site and read through the stuff that's relevant to whatever we're doing, because the visual aids there are amazing and they will give you insights that I can't produce with drawing. And I wanted to show you one, but fucking Regis computer doesn't work, so what a shock. What a shock. All right, let's just talk, we're gonna start off here pretty chill. I want to at least just address limits and continuity in the complex plane. And I think on Monday, we'll talk about differentiation, but please read through that section, because differentiation is, here's the good news. Differentiation is the same as in calculus, like when you do it.
Yeah.
The doing, yay, yeah, the doing it's the same, you've got that. What it means is a whole other thing.
Okay.
And so I'll help you see that, but it's like, it's a much richer thing than in Calc 1, even in Calc 3. Limits and continuity in C. So all right, so I've got a function that maps from a subset. So this is G, is a subset of the complex plane into the complex plane. Henceforth, I will just write, like our book, F has a domain of G, so this is the domain, and we're always going to assume it's part of the complex plane unless otherwise specified. This gets a little pedantic writing that every time. We have a freaking function. So let's see here. So if I have Z, you can also express this like this. This is the input, but this is the image of Z. We are going to be thinking of things visually in a way you probably aren't used to, like a rich visual interpretation of functions that we can only have because of the amazing realm we live in. So expressing these complex functions, it can be as simple as just writing out what to do with the complex number Z. Cube it, add twice that, you know, it's a polynomial there. That's a pretty easy thing to follow, at least computationally. So this is just kind of the most basic form. But it could be this very interesting form where we assume that the reader is thinking of Z as x plus iy, and then we do stuff with the components of Z. So see, now that's a whole different thing. It's like breaking apart the input Z, grabbing the real part and the imaginary part, and then doing new stuff with them. So that's another way we will express complex functions. And then we might also do this in a polar form. So we could just say that this is equal to something like r squared e to the I theta over 3 plus pi or something like that. And that's assuming that Z is written in a polar form. So with this, the underlying assumption is that Z looks like this. And then we just manipulate the various components in polar form to get that. These two are going to be the most common ways that we think about complex functions. I just want you to be aware of them. And I think we're probably only going to have time to do limits here. Maybe not. Maybe we'll have some continuity, because that's where the fun stuff comes in, the weird stuff. So let's just talk about limits first. We've got what we need. We say that the limit as Z approaches Z naught of f of Z equals this number W naught. So complex numbers. W naught has a real and imaginary part. So does Z naught. We say this is true if, and this is going to look familiar, given some positive number epsilon, we can find a positive number delta so that when 0 is less than Z minus Z naught is less than delta. This is a punctured disk centered at the limiting point of radius delta. So let's just make a little note here. This is, this looks like this. If this is Z naught, we're taking out Z naught. So it's punctured. We can't get to Z naught. Because remember, limits aren't about what happens at the point, they're what happens near the point. Limits and point behavior don't mix. It's near point behavior that a limit's all about. So I've got this radius here, delta, and I've got a little open ball around Z naught. So that is a, keep in mind,
Oh
punctured.
no, this is from every direction.
Oh yes!
Oh no.
There you go, all right, yeah, good, it started, yes.
I don't like that.
Yes, we're free falling right now. Fantastic. I love that. That's a good sensation. Isn't that why we come here to like live on the edge? So this is a punctured. Make sure you make a note. A punctured disc centered at the limiting point. And as Noah said, oh yeah, oh shit, that's a lot of ways to come in to the point. Indeed it is. So that when our Z is inside that disk, we have f of Z minus W naught, the output is less than epsilon. In other words, we have this ball centered at W naught. So here's W naught at some point. And I've got this ball of radius epsilon around that. If the Z is in there, then f of Z has to be inside here. And I'm going to say this again, just get this written down, and then I want to talk about this, because it's important and it's deep. This is, limits are all about a call and response. Have you ever been to like camp or something like that, maybe some church where they like call out, Kikari! And then you have to respond, Bakaka! Or something, I don't know, like that's the call and respond. I don't know, maybe we went to different camps.
We live very different lives.
I think so,
Yeah,
I think so.
Very different ones.
I think so.
Bakabakashi.
Yeah, so, call, or how about this, Marco,
Polo.
Polo, call and response. See, you've done that, we're not in
We
totally
could have
different
started
worlds.
with that example.
I could have started with that. It took a while to get there.
That's fine.
I was in the jungle. So call and response means you tell me how close you want to get to this output. I tell you how close you have to get to this point to succeed. So the call is the epsilon. Hey, can you make sure that all the inputs around Z naught are within this far of that point? And you say, yeah, because the limit exists, I can guarantee you this little neighborhood here, all the shit inside there goes inside here. And you're like, well, wait a minute, I want to shrink this. Are you sure? I'm going to make this a tinier disk. And you're like, yeah, I can do that. Just make a little tinier disk here. And then all that stuff lands in there. That's what it means for a limit to exist. Now, in the real line, back to Calc 1, limits are chill. Even they're still hard there. People still hate limits in Calc 1. And that's why we kind of barely do them, right? Because it's like that epsilon delta stuff is way too much for a Calc 1 student these days. It's kind of always been too much for a Calc 1 student. But in Calc 1, what did it mean to have a limit? So in Calc 1, we would say here's x naught and here's y naught, and this is y equals f of x. I would say to you, hey, the limit as x approaches x naught of f of x is y naught. That's what this picture says, because if I pick a little epsilon neighborhood, plus and minus, I can find a response over here, a little delta neighborhood, so that all this stuff shoots into there. But down here, there's only two ways to approach. Remember how you have left-handed limits and right-handed limits? Because there's only two directions. You can come in from the left, you can come in from the right. Over here, infinitely many ways to approach the point. You can even spiral in if you want.
Interesting.
So this, for this to happen, this is called stronger. So in limits in C are stronger. It's requesting more structure out of the math, out of the function than in R, and it's simply because you got so many options to consider. So that definition, you don't need to do a whole lot with that. Let me just kind of show you how this works. Let me do a little proof. So for an example, proof, and I'm not going to have you do this kind of proof stuff either in this class. This is like, that's real analysis. This class is more engineering focused. But let's say I asked you to prove the limit as z went to 1 of 3x minus 1 equals 5. Now, when I teach calc to my students, whatever calc we're doing, 1, 2, 3, I always say the way to do a limit is to plug and chug. If you can plug the limit point in and you're not dividing by 0, things are fine. Because I'm relying on a property we haven't talked about yet. But notice here that this thing, you probably would grok that that is 5 without me telling you. I hope you would. Danke. Schön. That. So you would have guessed the limit was 2 the way I had the damn problem written. Yes. So now it's 5. That's what I was thinking. So I want to prove this. So to prove this, you do a little scratch work. So let's just do some scratch. And this is the mysterious part. We're going to take a look at the f of z minus the w naught. So this is f of z, and that should say z there, not x, excuse me. And this should say, this is the w naught. So I kind of work from this epsilon part and see what it requires to make this happen. So from scratch, I just plug this in. F of z is 3z minus 1, and then minus the output that I'm claiming, 5. And what's cool is this always works out so well. And notice that I can pull a 3 out. And that is pretty hunky-dory because, check out here. Here we have z minus 2. And that looks like this piece here. So this is telling me that if I want to make that less than, if I'm falling over, less than epsilon, I can just make this less than epsilon. And then that helps guide me to what z minus 2 needs to be. So, in other words, let me write this out. Thus, if we want f of z minus w naught less than epsilon here, we just need 3 times z minus 2 to be less than epsilon, i.e. we need z minus 2 to be less than epsilon over 3, which is always fun to write, because you got epsilon and 3 opposing each other. They look like they're friends. And so this right here is my delta. So this equals our delta, because when z So you tell me you want that thing up there to be less, let's say you want epsilon to be 3. All I have to do is make z minus 2 less than 1. So my delta would be 1 in that case. This gives me a call. The call is epsilon, the response is this delta. So now that I've got a way to produce that, we can always find the corresponding delta. So we can always find the delta for any epsilon. And you just come up with this formula, and you give that to someone, and that is the proof that this limit exists, because there always is a response to the call of epsilon. I'm not going to ask you to do that, but I sure wanted to show you. Have y'all had real, who's had real analysis yet? Yeah? You did this in there?
Uh-huh.
Yes. You know, you taught it.
Wait, oh, that's right.
Yeah.
That was a long time ago.
No, it wasn't.
Yeah, it
It was
was.
2 years ago.
That's a long time ago, Noah. Was it only 2 years ago? Wow.
Maybe it was 3 years ago.
I don't know.
Who knows?
Yeah, yeah. I love teaching that class.
It was definitely after the COVID year. So
Yeah. So I
probably
just-
2 years.
Yeah, that sounds right. Okay, so let's see, what else do I want to tell you here? Oh! Once a limit exists, I think this will be our last thing, we won't talk about continuity today. Once a limit exists at a point, z naught, we get the same limit regardless of how we approach the limit point. We get the same limit value regardless of the path we take. So in other words, let's draw a little picture. Here's Z naught. Got some little delta disk around that corresponds to the output. So here's W naught over here. And I've got some big epsilon there. And there's this function f that goes between these two. Why am I not making a graph? Why am I not making a graph for like x and y axis? Why am I not doing that here? How many inputs do we have? We have 2. How many outputs do we have? 2. We need a 4-dimensional graph. We can't do that. So we can't actually graph complex functions in the way you're used to, because you've got 2 input dimensions and 2 output dimensions. Even in Calc 3, you're good, right? Because everything's just one output. So you can like go, oh, I've got 2 inputs, and it's some kind of weird surface here floating in space. Can't do that here. So there's all sorts of creative ways you could do that. You could like give the points a color and like a hue, like not a hue, but a value, dark and light values. And those can represent the complex values. But it all takes like imagination and never fully gets there. So in other words, if this is the case, you give me any epsilon you want here, I can produce this here. If I approach that Z naught in any weird ass way, no matter how I approach Z naught, no matter how crazed my path is, the output will approach W naught over here. Now why am I making that point? That's because that helps us show when limits don't exist. So this fact lets us show some limits do not exist. So in other words, if I can find 2 ways to approach the limit point that produce 2 output values, 2 different output values, the limit doesn't exist. So i.e., find 2 ways to approach the limit point produce two output values, two different output values. Writing's going to get pretty bad there. So let's take a look at a classic example. So that's z over z conjugate. Looks pretty simple, but the fact that there's a fraction starts to get a little sus, right? Like, fractions always create bad, and especially when the bottom goes to 0, and especially when I make sure that they go to 0. So we want to consider this problem here, which is just the limit as z goes to 0 of z over z conjugate. Let's write that in polar form, or excuse me, rectangular form. So x plus iy goes to 0. And then here we have x plus iy over x minus iy. This is going to help us see something. So my input space, in the input space, I'm approaching 0. We're coming into 0 here, and we want to see what's happening on the output space. So let's do this in a couple different ways. First off, let's approach on the real axis. So approach on R. And think about what that means. When I'm approaching on R, that means my z is x plus 0 iy. There's no imaginary part. So that when I come over here and look at that limit, the y is 0. We get limit, lim, as x plus iy goes to 0. And here we have, actually we've got just x going to 0, right? So x going to 0 because y is 0. Boy, that's loud. So we're only approaching on the x-axis. So and limit as x goes to 0, y is 0 there, of x plus 0i over x minus 0i. What is that limit? Let's simplify. Limit as x goes to 0 of x over x. What is that? It's 1, right? Because it's not, we can't plug in 0 because we're dividing by 0. But as x gets closer to 0, you've got tiny number over the same tiny number. That's 1. You can just cancel those x's. It's 1. But what happens when we approach on the imaginary axis? This is our last thing for today. It has to be, I think. So now let's approach only on the imaginary axis. So now approach on the imaginary axis. And when I say approach, I mean approach 0. So here's my input. And I'm going to come in just like this. Just on that line right there, just on that imaginary axis, come to 0. So here z is 0 plus iy, and we're going to let y go to 0. What does the output look like? Can you just take a minute? Let me give you a minute. What is the limit now as we approach this way? So you've got see -1 there? Yeah, check it out. Because this is 0, right? So the x is 0, and I put it in there just to be slightly tricky. And then again, the y's cancel, and you've got I over -i. That limit is -1. So as I approach this way, it's -1. As I approach this way, it's +1. And I will give you a fun fact that you might want to try. I can get any limit I want out by approaching the right way. I can produce any number I want as an output just by coming in just the right way. every direction of approach produces a different limit. It's pretty crazy.
What about like a spiral?
Yeah, it's kind of like yeah. I don't quite know, but I like the thought. But we'd have to work it through.
It just feels brutal.
It's like not one point there, but like multiple points. So okay, well, if we come in like this way, there's a point here. That's like, okay, that's where we're going. But there's
Yeah.
another point there. That's gonna be like,
Yes.
oh,
Yeah. Yeah, this function, this z over, was it z conjugate at the bottom? Yeah. This thing's pretty weird.
yeah,
If like, this is a pretty messed up function, especially right on at 0. It's pretty weird. All right,
that
good
feels
stuff.
illegal.
Yeah.
Yay! When you tell me, you're just encouraging me when you say it hurts my head, or this seems wrong. That's what I'm here
Okay,
to
you're
make
not
you say.
challenging me enough.
I'm not challenging you? No?
I feel discouraged now.
No! Are you not challenged enough?
No, that was a joke, because you're like, whenever you
Okay,
complain about things, you're
I'm
challenged.
scared. Well, I worry about that. You're
No.
tapping into my deepest fears
No,
now.
I'm good.
You like really knew how to go straight for the jugular.
Yeah.
Like,